Hello. Hopefully my mic setup is all correct and everything. It's been quite a while since I streamed. Oh, it turns out I've got my own audio coming through. Why have I done that? Terrible idea. Hello. How have I managed that? I can hear my own voice. Oh, that's why. I had the stream open in a second tab. Hilarious. That's a bad idea. Right. Okay. So as usual, I start the stream and have nothing set up correctly, but whatever. Hopefully you can all hear me. And everything. So yeah, the plan is to build a haze detector. So basically, when I'm running, when I'm doing laser stuff, I obviously fog the room out and everything. So yeah, having some idea of exactly how hazed the room is quite useful, and also because I get distracted easily. So sometimes I leave the fogger on and it gets too foggy, which can mess things up. Because if I'm recording laser stuff, having too much fog can make the beams be less defined, and it kind of glows the room up a bit because there's a lot of light dispersion, which tends to kind of increase the ambient light level. And what you really want is like low ambient light level and just the beams being visible on the recording. So the thing about fog is it's really just like a lot of different particles, like tiny little particles. And you can also think of it like humidity, because it's largely like propylene glycol or ethylene glycol. And oh god, this song is horrendous. Sorry, skip that one. There we go. Yeah. So yeah, it's like water and propylene glycol basically just hitting a heater and being dispersed out into the air. So you would think that like something like a PM 2.5 sensor or something like that would be a good option here, and it kind of is. But it's also then picking up things like dust, which is yeah, a problem, because I don't want to pick up dust. I want to pick up just fog. So one thing that's an option is to use the absorption spectra of the components of fog fluid as a mechanism of detecting exactly how much fog there is in the air. So a way to do that is you have a tube made out of quartz glass. Now, quartz glass has like a really good transmission spectrum. Like there's almost nothing that it absorbs apart from like some really weird wavelengths. But as far as I'm aware, like everything UV down to IR, it's pretty damn good at transmitting. And then what you do is you have an emitter on one end and a detector on the other. And I'm actually, oops, that's, oh, there we go. Flying around. Draw that. And I'm going to draw two. In fact, you know what? I'm going to change the color of this because, and you'll see why in a minute. You can probably guess. Excuse my horrendous drawing. So let's make it all red. So what you then do, you get a fan. That's a horrendous drawing. And basically what happens is the air gets drawn in through here, blown through this tube, and out the other end. Now, you don't necessarily need the tube, but the reason I want to do that is because ethylene and ethylene glycol, propylene glycol. I think it's propylene glycol because ethylene glycol is poisonous. And vegetable glycerin, which is also in fog fluid, is kind of sticky. And I think it's kind of conductive. So what I actually want to do is have the air blown through this quartz tube and then have the electronics external. So the quartz tube is just basically the a vessel for the air to go through, and the rest, and all the electronics are then kept nicely clean and out of the way. Now, the reason I've drawn red and purple here is because IR and UV are good options here. So I did a bit of digging pre-stream because I knew I was going to do this. So one moment, let me just switch over to this one. So this is the UV and visible spectrum of it's mostly visible, but it goes down towards the UV spectrum of propylene glycol. And this is the top left one here. And you can see that towards 400 nanometers, the absorption just goes through the roof. Now, this graph's a bit crap because you can't really see what's going on beyond that. So this one's quite nice. So this blue line is ethylene glycol, and the cyan line is glycerol. So you can see that like around this like 350 nanometer and below, and particularly with the ethylene glycol, it comes over to towards this side. Obviously, propylene glycol isn't on here, but it seems to be that all of the sort of glycol and glycerol stuff is very similar. So you get this absorbance in the UV spectrum here. So that basically means that if we've got a UVB or UVA source, preferably UVB, then the light that passes through will be more heavily absorbed in this spectrum. Now, looking over towards the IR spectrum, so this is polyethylene glycol, which again, slightly different. I'll zoom in slightly because I think this is getting crushed a bit by the stream compression. But so you can see here there's this wonderful peak around like 1080 to like 1140-ish nanometers, where it just goes like the transmittance. So this is reversed from here. So this is the absorbance, which means that as it goes up, you get more light coming, more light absorbed by the material. This is the opposite of transmittance. So basically, at around like 1100, like 1120 nanometers, the it just goes through the floor really. And then if we go over to propylene glycol, because this is polyethylene glycol, this is propylene glycol, and it's about the same. You can see this like 1000 nanometers, then you come up a little bit, and you're around like this 1100 mark, and it really the transmittance really goes through the floor. So that's useful. And also, if 1100 nanometers turns out to be a problem, we can always go all the way up here to like 3300, 3400. Although things get a little bit more expensive that end because the detectors tend to be a bit pricey. You know, if you want a photodiode with a center frequency of like 3300 nanometers, you're looking at about I think the cheapest one I found was about £50 for a diode. So yeah, I ain't paying that. So this thing, the VML 6075, it is no longer manufactured. However, it was very popular for a while. So there were breakouts from SparkFun and a couple of other places. So you can still get them, the little breakouts on eBay. I may end up using them. I might not, but this seems to be one of the good ones for UV. So the datasheet. So this is a true UVA and UVB sensor. It's not like a violet sensor that pretends to be a UV sensor. So if I just scroll down, here we go. We can see the typical output, and you can see it's this UVB peak hits around like 330-ish, and then the UVA hits around, I don't know, about 360-ish. So it's like 330, 360, about that kind of range. And then if we compare that back here, sorry, that's the wrong one. That's like the 330-ish peak is well within this absorbance area, and it's kind of the left side of this graph. This one is actually for propylene glycol, and then this one has ethylene glycol and glycerol. So it seems like they're all very similar. So for the UV side of things, that's pretty cool. That covers us quite well. And then on the IR side, we need something around the sort of 1100 nanometer range, maybe like 1050, 1080, that kind of range. So I started having a bit of a look around. Now 1050 nanometer emitters are pretty decent, like pretty easy to get a hold of. So yeah, we got this very cheap, just a couple of pounds, and there are quite a few options here, but yeah, this is 1050 nanometer center. It's actually a little wider band than that. I think on the did I have the datasheet open? I did. So the wavelength here, yeah, I think for some reason it lists itself as a 1050 nanometer emitter, but I think that's just because it goes as high as 1050. So you don't get a lot out at that range. It's more at the yeah, 450. Actually, that's very weird. I'm not sure why this is listed as very strange. I'm not sure whether this is correct. I hadn't noticed that graph before, but that's very strange. Like, why would you list yourself as a... Oh, here we go. So, okay, so it's got a range of wavelengths. Very strange. But anyway, the point is that as long as the receiver is fairly selective, or the other option is to put an attenuator on. So, say for example, anything under about 750 nanometers, you start a roll off where you don't end up transmitting that light. Because really what we want to know is that there is some 1050 nanometer light going through there. Now, this is all going to be in an enclosure, so like there's not going to be any random IR or UV just like coming into the device. You won't be able to actually get any light in there. So any amount of emission in that range should be fine. It is a shame that it's not actually peaked here. I'm not sure why that is. It's a bit weird. It seems to be that a lot of these devices, when you look them up, they're listed as having like peak wavelength of some high number. This is on the photodiodes as well. And then when you actually look at the datasheet, the peak wavelength is nothing near that. A lot of it's just a bunch of bollocks. So I've ended up generally searching for stuff that's like way beyond where I need, and then it actually has the emission there. So what I might do actually is see if I can get an IR emitter that's a little further over in the wavelength, if that's even possible. Oh yeah, it does look like it's a possibility. So we want around like 1100 nanometers. So if we say, yeah, anything above that, including the 1060, 1060s. Yeah, so you're going to show me the results. Thank you. Yeah, you can see it gets kind of pricey. Yeah, I'm not paying £18 for an LED. Fuck off. I'm not paying that much money for an LED. So yeah, unless it's ridiculously bright, which it isn't. Yeah, so it does kind of get ridiculously pricey when you get up into this range. But these are cheap. Like, these are really cheap, and I am quite happy to put up with the fact that only what are we on here? 0.03? No, 0.003. So that's what? 0.3% of the optical intensity of this light. But it is a that's 350 milliamps forward voltage. So the peak wavelength here is going to be very, very bright, which means that the luminous intensity out at this range is still enough. There's still quite a bit there. So on the photodiode side, I've been searching around through some of these. This one might have been pretty good. Or was it this one? Oh yeah, this one was pretty good. So yeah, this one's pretty good. So this is the photodiode that I would be using for measuring the incoming light from on the IR end of the spectrum. So I think like a high pass, an optical high pass filter might be mandatory here. Luckily, I don't think they're like crazy expensive. I mean, yeah, if you want like really, really high end ones, of course they are. But in this particular case, it's just crude. It's fine. But yeah, effectively, what I want to do is then have. So this seems pretty good. This is like what 25-ish% in the range that we're talking about, which is fine. And what I will probably end up doing as well as this. So I mentioned that if I just switch back to the drawing, what I will probably end up doing is having a normal emitter here, and then a standard light level sensor. So this will be like a white LED or something like that, probably. And then just a standard light level sensor. And the idea is that the one LED will turn on. So this is IR, and this is UV. So they'll turn on in sequence, and then a measurement will be taken from the other side. And effectively, what it'll do is it'll measure the IR transmittance, the white transmittance, and the UV transmittance. Effectively, it's just light levels. Or at least that's the goal. So yeah, that's the idea. And then this will all be put in an enclosure, as I said, so in a big box. And this will go in there. There will be a little ESP30, either ESP32 or 8266. Probably an 8266 because I don't need any of the fancy crap that a ESP32 can do. So yeah, that will then connect to these, and obviously there will be some circuitry in there, which basically does all the analog gubbins that need doing for the photodiode side. The white LED detection stuff and the IR detection side, which, where were we? That was on the, yeah, so the UV, that's it, sorry, on the UV side, this is I2C, so it's a tiny little package, 2 by 1.25 millimeters, so it's a tiny little thing. But yeah, this will all be I2C anyway, and then the visible light sensor as well will be also probably I2C or SPI, although I2C wouldn't make sense because, you know, if I've already got that bus, I might as well do that instead of breaking out SPI bus. And then I think the UV side is the only thing that requires, sorry, not the UV side, the IR side, that is the only thing that needs any like magic circuitry going on in there. Yeah, so that's pretty much what I'm going to do with this. And this the UV light sensor, it's got 16-bit resolution, which is pretty good. But the thing is, so the resolution is good, and I will probably get some pretty good resolution on the UV side, on the IR side as well, just by using a decent ADC. I can't remember what resolution the built-in one is for the ESP8266. I think it's 12-bit. But there's a great way to improve this design without needing any fancy high-end ADCs and amplifiers. And it's actually the same trick that false color X-ray machines use. And basically what you do is, so this is the forward current on the LED, and this is time. And what you do is you let's just go with green. So you can do it either direction, but basically what you do is you for each of the LEDs, you pulse the forward current on the LED in steps. So you first pulse a tiny bit of forward current, and then you take a measurement, and then you pulse a tiny bit of current again, a bit more current, and you measure again. And what you're basically doing is you're increasing the light intensity level for each one. And that way, when you measure with the receiver, measure the light level with the receiver, you actually get a better range of measurement because your light levels are changing. So yes, it's still the same resolution on the other side, but whereas you might not be able to tell the difference between, particularly on a short transmission length, like the tube diameter is only going to be maybe 25 millimeters or something. The ID on the quartz tube is only going to be about 25 millimeters, maybe 30 or something. But the idea is that by having a low brightness flash that you measure, and then a medium brightness, and then a high brightness, or some number of steps, you can kind of measure how much brightness you needed to put in before you even got a measurement in the first place. So even if it's without, like, beyond the normal measurement range, you can get a bit of a nicer effect that way. And what I can basically do is in clear air measure all of the normal responses for this, and then basically uses that as like de-embedding. So effectively, you start off with clear air, and then you test that, and then figure it out, and then you can then just fog the hell out of the room. I've got a couple of 1.5 kilowatt fog machines. I can just turn them way up. I think this room is far too small for. Even one of them will render the room like completely opaque within a couple of minutes. So run it really, really hard, and then take the measurements again, and ideally graph them over time, so that we get a sort of resultant spectrum. From that, what I'll probably end up doing is making that just spit out some data over Wi-Fi, just over HTTP, and from that I can then use a DMX USB to DMX adapter, and actually keep the fog level at a level that I want. So I can configure the fog level to a particular like haze density, whatever measurement I want to use for that, and go from there. I still don't want to go with the PM sensor, but I might couple it with one, just to see if I get some good results out of it. I suspect that the ambient particulate level in the room varies an awful lot. Like for example, if you've recently like hoovered, vacuumed the floor, that kicks up a bunch of dust. If you've done a bunch of sorting out, that kicks up some dust. You know, moving in and out of the room, the particulate levels are going to change in the room over time. Whereas with a optical approach that uses UV and IR, we're relying on the specific spectrum, the absorbance spectrum of the fog fluid, which is quite nice. And of course, with the white light as well, and the light, the brightness sensing there may well be some value in having that. I don't know yet, but it's so cheap to add as an additional part. So mechanically, what I basically need, because obviously these boards have got to go on two sides of a piece of quartz glass. So it can't be one PCB really. It's got to be two. So what will happen is there will be a PCB with the, and there will be with the LEDs on, and there will be a PCB down the bottom. And I'll probably just use like, I don't know, wood or something. I don't know. I might even just zip tie them to the glass. So basically just arrange them around the tube and then just zip tie both ends of the PCB. And the thing is, they don't actually, the PCBs don't need to directly talk to each other because they're both going to the microcontroller. So having access to both, like one being able to talk to the other is not necessary. So there's no wiring or anything that needs to be done that way. It just goes over to the SP8266. So that's useful. I might see if I can. I can never remember whether JLC's pricing on what are they called on when you've got two designs on one PCB paneling. Yeah, I think their pricing is fairly cheap, and to be honest, these PCBs are going to be really small anyway. The main thing that I'm worried about is with this particular thing, like that is tiny, 2 by 1.25 millimeters. Really don't want to solder one of these. So what I'll probably end up doing is for this particular device, use a breakout, because there's nothing like really critical that says I have to have it all on one PCB. Just having a little breakout for this should be fine. And as far as I'm aware, so this is the SparkFun version of it. What is it? It's the Vemel 6075. There it is. So yeah, like it's not going to be a problem just to use that. Like I don't know how big this PCB is. They got any mechanical information? I think I looked before, but yeah, I have to get the Eagle files, and I can't really be bothered with that. But I mean, if that's 2 millimeters, it's like what, 4? Yeah, it's probably like an inch by an inch. I bet it is. It's an inch square. Yeah, I could get a stencil, but I'm lazy, and you can buy these on eBay. without the silly connectors on them. Like I get that if you're doing quick stuff, then you can just plug all this stuff in, but like there's no reason for me to do that. So yeah, I think just having one of these is probably fine. Like, yeah, this kind of thing. Oh yeah, that's a good point. These have the pinouts on them anyway. But yeah, so that's not a problem. And then this is kind of the, you know, I'm not mass producing this thing anyway. How to be able to point it at not sure how I mean, I'm probably just going to zip tie this thing to zip tie this to the glass because I'm lazy. Like this and the other PCBs. It'll all just get zip tied, I think, because they only need to be kind of opposite each other. They're not like lasers. They don't go. They got a fairly wide. I think they're like the LEDs I've been looking at are all like 60-degree angle, so you've got a ton of room to work with there. Now, the one thing I am kind of worried about with this is if we go back to this. So, what I'm kind of worried about is use that one. So, you got a glass tube. No. It doesn't matter if the light escapes. The light can go anywhere. Basically, what I'm doing is shining a light through to a receiver. Yeah. So basically, the gas, the foggy air goes through the center of the tube, and then the light is just basically going through. Now, what I am slightly worried about is a fiber optic effect, where basically you get whatever. That's a imagine if light moved like that. But yeah, you get what I mean. Like you would get this like light basically tunneling itself through the wall of the glass, and that is somewhat of a concern to me. Unfortunately, I don't have an answer for it. Like, there's basically nothing I can do short of. But the thing is, like any inclusions in the glass, like minor inclusions, even if I shone a laser beam, like even if I did this with like an IR and UV laser beam, you would still get beam scattering through the glass. So, short of like, I don't know. Yeah, the problem is that plastic has a horrendous absorption spectra. Like the IR and UV absorption of plastic is pretty crap. Like it goes all over the place. Like so it's not so bad for IR, but UV it's horrendous, and it often degrades plastics as well. Whereas with like quartz or borosilicate, but mostly quartz glass, it's not so much of a problem. I suspect that this won't be too bad because most of the light is gonna go through here. Like the amount that's like the absorption of the glass as it passes around here, like you're gonna get less bleed through here, I suspect, than go through that. Yeah, like literally the other way to go is like two hemispheres of quartz glass with like a blocking thing in the middle, like plastic thing. I just don't see it being that much of a problem, to be honest. Like it might be, but I suspect it's probably fine. So yeah, like I'm not going to worry too much about it. Now let's go back to the monitor. So I know that measuring brightness of an optical source with a photodiode is a thing. I can't remember how to do it. I believe you reverse bias it with a small amount of current, and then you measure the voltage drop over it, I think. Or you measure the current that flows through with a shunt resistor. Let's find out. Photodiode. Photodiode circuit. Right. I know you can bias it as well. Yeah, this looks about right. Yeah. So like this looks about right. I know you're biasing it with a small amount of current, although that's weird. But yes, so that seems doable. I'm gonna have to look at some design guides because I know that this is like quite well tied into the specifics of the photodiode in terms of like the like how much bias current you want and all of that. So was it this one? Yeah, this silicon pin photodiode. Again, I think this is really small as well. So that might be another interesting thing. Very small. I like that. Like, yeah, you're just gonna tell us exactly what package it is? No, it's just a very small SMT package. Useful. Very useful. We know it weighs 3.8 milligrams. That's useful. Oh, okay, so it's 3 millimeters long. That's not fun. That's not a problem. Should be okay. But yeah, so you get this. I mean, the dot current on this is measured in picoamps, so that's I don't need to worry about that. So where are we? So about 2 to 3. This graph is confusing. Like, why would you make a graph where you show the 2, but don't and like all of these are completely variable in size, like 0.2 to 0.3 versus like what? This is a terrible graph. So I guess about 2.5 microamps. Although this is at 5 volts, and I'm more likely to be using 3.3. Yeah, it is. It's a garbage graph. Like, if it was log 2, this bit would make sense. But then it just goes all over the map. Like, what is this garbage map? Oh, look how linear it is. That's what they're doing, isn't it? They tried to make it look really linear when it's entirely not. Like, I bet if I typed all of these points into a graph, just like a normal graph, and it just look. Yeah, like, is this even proper log? Oh, that's a bit more. Oh, excuse me. That's a bit more reasonable on the x-axis, but yes, horrendous. Okay. So, that's doable as well. Fun. So, yeah, I think this is doable. So, I couldn't decide whether to do some circuit design or mechanical design first. And I'm kind of tired. It is 1 a.m. here, so I will probably not do a whole lot tonight, but quartz tube. I don't know why I did that. eBay. So yeah, you can get these as like pond filter tubes. They're quite useful. The reason that the pod filter tubes are quartz glass is because they use UV sterilizers, or at least UV clarifiers, they call them. Which means that, luckily... yes, I'm going to select my glass tube by wattage. What kind of nonsense is that? Alright. I suspect that there's some standardization. So that's what, 35mm? That'll be OD. Yeah, because part of the issue is I don't want this thing to be massive. Like I ideally want like a small, like a not very long quartz tube. What's this? Yeah, like a quartz tube, but maybe only, I don't know, like 10 centimeters long, maybe, but 35mm wide. I don't know. These seem to have like a rounded end on them, which is a problem because I need to be able to get the gas through. So yeah, that's not ideal. Okay, well, so let's make some notes briefly. Yeah, let's full screen this. Okay, so it's going to be zoom in so you can wait. Kind of weird zoom levels of that. Right. You say I could cut the end off, but you know what's going to happen if I try and cut the end off, don't you? I'm gonna go and buy some sort of glass cutter or something, and yes, glass in the fingers, exactly, and also just completely shattering the glass because I will just completely fail at it, and it will just smash immediately. So ideally, I want a clear tube. I could probably give it a go at least, but I would prefer not to. I would prefer just to, have a glass tube. So, I think actually 40mm ID is a good option because that can tally with a 40mm fan. Because getting a 35mm fan is kind of weird and annoying. But getting a 40mm fan is much easier. So, and the good thing about that is that, yeah, it's a 40mm fan, which is small and usually very whiny because tiny fans are whiny. But a mid-size, a slow, like a low RPM, low current, 40mm fan should be fairly quiet. So that should be fine. So then, yeah, Noctua's 50mm ones are pretty good actually. Yeah, you are right. I mean, the thing with the 40mm tube is that if I used a 50mm fan, I could definitely have a reducer. Yeah, sure, that's fine. Automod might like complain. Let me actually. That's a good point. Have I added you as a trusted whatever? I always forget how to do this. Oh god, yeah, it's just literally. It's killed all of your. I don't know how to undo that either. Bear with me one moment. Let me operation. I always forget how to do this with like Hmm. Somewhere in here there is a thing about... Oh, is this in Streamlabs? I bet this is in Streamlabs. I bet you have to do it separately in Streamlabs because of the Streamlabs moderator. Yeah, that's it. This is weird. So I know I have Streamlabs set up, but it's just asked me to like... Very weird. Okay. Oh, I have no idea. Very weird. Oh, here it is. I'll go away. Here we go. I believe I can add you as a regular now. To be confusing. Oh, now I can't find you. I'm now very confused because I can't find the mod action that was just there. Oh, who knows? I'm gonna faff about with it too long. But yeah, yeah, I think I've added you now as a regular or whatever. Sorry for the benefits of when this goes up on YouTube. That last bit was messing with Twitch moderation because yeah. Okay, so I'm not going to be using Quartz Tube, and it will probably be a Vemel 6075 for UVA and UVB. So then probably Spark Fun Breakout. Then where are we? Yeah, I might end up using this one. SFH 4735 for IR. Yes, IR. Spectrum is interesting. Okay then. Yeah, Spectrum is mostly lower than 1050 millimeters, but yeah. God, 350 kiloamps, Jesus. Yeah, no, that would be bad. Okay, so then on the what was it? Yeah, so this is this is the one I was looking at here. Was this the? Yeah, this is the one that I was looking at for. IR, right? Yeah. So this is the SFH 2700 FA. Oh, okay, so they're both by Osram. Was it 25% or 20%? Oh god, not even that. So 8, 9, 10, no, 8, 8500. Yeah, okay, so these are 500. Yeah, 500. Wait, no, sorry, 50. So 1050. So at 1050, we're talking 35%. And then at 1100, it's way down at like 15%. But that's fine, because there's not going to be any other light coming through. So consider and UV so I think having the optical pass filters on the receive side makes actually more sense than on the emitter side, because if there is any stray light that comes through into the tube, then having the filters on the receive side helps there. There shouldn't be any stray light, but obviously there's a there has to be a path to the outside because of needing to get the air through, and having like a complex labyrinth maze for that seems like effort. So yeah, IR and UV optical pass filters on the receive side. Cost this up because I suspect that could get quite expensive, and I don't want to pay a silly amount of money for that. So yeah, is this the same one? Or do I have this open twice, or do I not? Looks the same. Oh yeah, hashes are the same. So for some reason I have that open twice. And yeah, okay, so we know we got the breakouts for that. So did we get a... So we got the IR emitter and the IR receiver. So let's put this here. So I need a UVA and a UVB, particularly the UVB side emitter. And UVB LEDs are notoriously not easy to get hold of. Now, that said, there is a new lighting technology which I thought was pretty cool, which is it's actually become a thing because of phones. So LEDs are kind of actually not great for infrared illumination of faces for and I know this is UV, but yeah, UV LED. Sorry, IR LEDs are like not great for very narrow frequency illumination of faces for like subject analysis stuff for cameras. So when phone cameras take an infrared picture alongside the visible light picture, it can offer like a better idea of where that face is in order to do like focus detection and a bunch of other clever magic. So what they've actually started doing is there's a kind of new optical technology. I don't think it's actually like new, but it's more that the parts are becoming commonplace and not crazy expensive. And they're actually based on lasers. So it's like having a tiny laser emitter, but it's not collimated like a normal laser. It goes. I don't know whether there's some optical magic or what. But yeah, like the output of that is yeah, it's quite wide. I think it's about like 80 degrees or something. But it can be a single wavelength, which is really useful. Saw someone the other day while I was looking for something else. I just realised I'm looking in the emitter modules, which makes them a little more expensive. Yeah, like 12 quid for an LED. Here we go. UV emitters. So, what was the wavelength range here? Further up. Yeah, it's here. So we're talking like 330-ish. 330-ish and 360-ish. Well, I mean, sort by the cheapest. No, I don't want 8,000 of the damn things. Yeah, that wavelength's not good. Oh, here we go. I can just search by wavelength. Yeah, you see, here's the problem. The lowest I can get is 365. And they're £5. Tiny LED. I bet the spectrum's crap as well. I bet it says 360, but it's... Yeah, exactly, look. They said, what, 365? Oh, I suppose that is 365. That's not bad. Not great. But... yeah, exactly. Like, that's perfect for the UVA. Like, I mean, look, that's spot on. So, I guess that answers this one at least. So, copy paste. For UVA emitter. What's the forward voltage and everything on this? I don't want the reverse voltage. Okay, so DC forward current 30 milliamps. That's fine. That's perfectly fine. 30 milliamps at 3.3 volts. Oh wow, that makes things very easy. I mean, like, I literally have a 3.3 volt supply, so yeah, okay, that's perfect. Okay. Yeah. Okay, so that's at least the UVB side. Sorry, UVA? Yeah, UVA side sorted. Laser? Yes, exactly. Like, this might be a job for a laser. No, not with 2 R's. Laser. Find out if they can go that low. No, they don't have them that low. I know I can get UVB lasers. That's a good point. Aren't on Blu-ray? Ah, 405. Okay. Yeah, blue violet lasers. UV lasers are heinously expensive. This is true. Well, I mean, all lasers are heinously expensive, but so what are we looking for? What was the peak wavelength? 330. This is not a useful result. I searched for 330 and you give me 405 everywhere because useless. Okay, so we might still be in LED town, so to speak. See if I can find one on RS because they sometimes have a slightly better range. Mauser seems to have a really good optoelectronics section actually. Like a really good optoelectronics section. Let's go with peak wavelength. There we go. That's what I'm looking for. Oh wow, 265 nanometers. That is yeah, a little lower than I was looking for. It's kind of bonkers. So let's go with about 330. Where were we? Yeah, 330. Oh. Like, they can sell me a 265 nanometer LED, but it jumps from 285 to 360. Arseholes. Woo! That's steep. Oh, that's cheap. That's... Oh, on a reel of 500. Okay, £5 is doable. It's pricey, but it's doable. Let's see what the emission spectra looks like for that. Yeah. 375 is not too bad. Where are we? So it peaks at this peaks at 275, which might mean it's no good. Oh wow, no, that's quite broad. Ah, no, because we want it about 330, don't we? Yeah, by the time we get down to about 300, that's like... Is this UVC? It is. Huh. Okay, UVC LEDs got cheaper. Because they didn't used to be this cheap. Although, yeah, £5 for one. With 13.5 milliwatts of radiant flux is great. Thor Labs. Yeah, I don't know whether they ship here though. Okay, let's have a look. Okay, so they do deliver here because all the prices are in pounds, so that's good to know. Yeah, okay, so the deep PV ones are ridiculously pricey. Wait. What did I load up here? And then what did I load up here? Is it the same thing? Why have I got this open 3 times? Weird. Okay. That's £43. Very expensive. Holy crap. Yeah. Have you got a part number for that 375 one? Yeah. Like, oh. Did I just click the wrong thing? Oh, do I need to click that? Where are we? That? There we go. Okay, that's doable. Oh, and the one afterwards is also pretty good. And so wait, hang on. So the 370E is cheaper and brighter? Wow. Hmm. I mean, both of those are pretty good. Like, that seems fine. I mean, it's... Yeah. I don't know. That looks like a standard package to me. I know it's like this weird, like, yeah, T1 3/4, whatever that means. But it's a standard-ass looking LED to me. Oh, it's got a spec sheet. Here we go. Let's have a look. Wait. Oh, okay, yeah, yeah. Ah, good. I'm told not to use trichloroethylene on it, because I was definitely going to do that. Whatever. Oh, but this is still... Oh, okay, yeah, but that doesn't actually help me, because the... Aren't we looking for, like, way lower than that? Like 330? Yeah, I forgot we were looking for 330. There it is. Yeah, here. And this doesn't have any 330. Yeah. Yeah, there's like 0 at that point. Yeah, and literally as soon as you get down into the 340 range, the price goes through the roof. So what was the data sheet on the 375? Actually, yeah, no. Yeah, that just goes at the 360. 330? Not on the 370 or the 375? Because both of those I just looked at. That's the spec sheet. So that's the 370. Oops. Spec sheet. So here's the 375. You hit 0 at 360. And then here's the 370. And you get a tiny, tiny amount, about 355, and then it's just flat. So yeah, there's nothing down below that end. So the broader spectrum of this one is slightly better, but yeah, that doesn't really help me there. Well, I mean, so what, like DPSS? Like frequency halving? Yeah, I mean, that's how they make green lasers, right? You start off with a infrared. Wait, frequency doubling, sorry, because it's halving the wavelength. I mean, you would need a 660. Because, like, you just shifting it by non-integral amounts, I don't think is a thing. I mean, maybe it is, but not that I've heard of. But yeah, like, frequency shifting, yeah, like frequency doubling, therefore wavelength halving. It's how you do green lasers, because you start off with double the wavelength in the IR, and then you yeah, the DPSS part of the optics halves that frequency, which is which is the problem though is that I don't think just getting an arbitrary frequency like DPSS optics setup is a cheap thing. I think it's only cheap in a green laser because it's mass produced. And I also suspect that it's not just a generic thing in terms of frequency response. I think if you go down towards the UV wavelengths, I suspect it gets trickier, considering how expensive a solid state UV laser, like UVB. World's first solid state UVB laser, January 2021. So yeah, that's gonna be more than I can afford. That's a shame. I mean, I don't really want to use a UV lamp like a vapor lamp. That seems like a shit idea. Like, if 360 nanometers is enough, like, where are we? Where was that spectra? Here we go, in the UV range. 360 should be just about enough. Like, that seems... Oops. Sorry, one moment. There we go. Like, 360 on its own might be okay. Why must things be expensive? Why? Thing is, like, I could put up with a ye olde lamp if it wasn't for the bit where I want to be able to turn it on and off, on and off, on and off, on and off. And if I remember correctly, with UV, with the lamps like that, it's the powering them on and off that has the most wear on them. So if they're just operating continuously, it's not quite so bad. But if you're continuously on, off, on, off, on, off, on, off, it gets kind of annoying. And also, I think you have to drive them in with like a fair amount of power, which would suck. Like, I don't want a big... yeah. It also means worrying about, like, what kind of enclosure I use. Because UVB is not too bad on plastic, but UVC is horrific. Like, it really embrittles plastic. And also, I have to worry about my eyes and my skin. But yeah, I don't know. Like, yeah, I know you can get a UVB tube, but they're pretty. Actually, I can't remember. Are they broad? In terms of spectrum? Oops. Broad in terms of spectrum? I'm not sure. Okay, so a UVC is very narrow, and then a UVB is fairly broad. Interesting. Yeah. Hmm. Yeah, this is a little annoying that you. I wonder what the reason for not being able to find, like, for the cost of uh UVB LEDs being so high is. Hmm. Yeah, but I really don't want to be. So, I mean, a lot of those are mains, which means switching mains, and I'm lazy. Hmm. Yeah, but UVC, like UVC sterilizing, is a real thing, and like the um yeah, like even outside of, like, that gets used a lot in industrial process stuff, uh like food and whatever. Yeah, I guess. I don't know. Like, you would think for the sterilization stuff, the UVC LEDs would be really common. I wonder if there is an actual, like, oops. I wonder if there's an actual, like, physical reason why it's difficult to get good ones. Like, I guess, yeah, part of it is also going to be economy of scale, but no, I didn't look. I did not check LCSC. Oh, is their website still broken for me? Their website was broken the other day. It was annoying me. Oh, I'm gonna have to go to bed in a minute because I've got a call in the morning. But let's quickly have a look under Optos. They got IR LEDs here, ultraviolet LEDs. Here we go. Because I actually wonder whether, like, rando Chinese suppliers I've never heard of might be a better option. Yeah, I mean, like, this is already more promising. Yes, but have you seen this? This thing is the best. So it's a client-side parametric search for JLC, but it's effectively for LCSC. I'm quite happy with this thing. It's quite cool. So yeah, you can search for pretty much everything parametrically through this. Yeah. Well, that's amusing. So the chat thing in the Twitch dashboard does not actually let me chat. Not very smart. Eh. Nope, not self-hosted. There we go. But yeah, for the YouTube folks, it's yaqwsx.github.io/JLC parts, and it's freaking awesome. I also made a thing for. It's a good point. Do I not have that script in? I thought I had a. Oh, here it is. Huh. Why is this not recognizing? Oh, there we go. That's it. So, yeah, there's I made a Tampa Monkey plugin that should, although I think it's broken because I haven't updated it in a while. But it should tell you how many. Oh no, here we go. Look, LCSC part number. Oh no, that's LCSC part number. That's not it. It should tell you the JLC stuff. But yeah, my user script is broken. I need to update that one. But yeah, I wrote a user script that basically when you go on LCSC, it tells you whether parts that you're looking at on here are in stock in JLC, and whether they're like regular or extended parts. But yeah, whether you got any whether like standard or extended parts, and what their pricing is, because the pricing is often different to what LCSC show. And I have another user script. Both of these are on my GitHub, but I have another user script that does the opposite thing, which is if you're on JLC's parts library, it looks up the parametric info, I think, from. I actually can't remember what that one does. I think it looks up the parametric info for the parts from LCSC and then shows them you in the JLC parts list. But that parametric one is really, really good. Like, that's one of my favorites. But anyway, yes, let's try. Did I already filter by? Oh, are there really just like 60 products full stop? It's not a lot of products. Again, there's this weird gap, look. Like, you get this, like, 300 to 315 and then 360 to 370. Very weird. Okay. Yeah, you can't even sort by most of these. But it's super weird because this is like... yeah, the forward voltage is 6.5 volts as well, which is interesting. But these are cheap. Like, this is 80 pence. They're going to give me a spectrum. Ooh! Okay, we're getting closer. What's this 305? Okay, this is £1.96 for one. And this looks a bit more promising. Perfect. Right. Okay, it's not perfect, but about 5% of the light is towards this 330 peak, which might be okay. I think it's the first LED I've found at all that hits the wavelength that I want. Like, in fact, I think that's the only LED I found so far. So thank you, Silverlight, not the terrible Microsoft attempt at replacing Java applets in the web browser, but Silverlight, the Shenzhen Silverlight technology is co-limited. Interesting. That's kind of cool. So, what's the 100 milliamps? It's quite a lot. Like, I can't read Chinese, so this doesn't help much. But at least they've got it in English as well. But so typical forward voltage 600. Okay, so typical forward current is 100 milliamps at 6 volts. That's a lot. So at 100 milliamps, we've got 14 milliwatts of optical power, which is fairly reasonable. Of which about, have a look at that. So the UVB starts to get around 50% at. Oh wait, are we on the lower side? I think we're on the lower side, aren't we? Yes, we are. Okay, so on the lower side of it, we need up towards about 310. Oh. Okay, so that doesn't actually help us all that much. Oh wait, no, this is the wrong LED. This one. Oh, no, this is great actually. Yeah, because this is like 310 through to 330-ish is where the peak is. So 310 is about here. So that's about 15% maybe, just a little under. And then 320 is here. About 50%-ish at 320. Garbage day. So okay, at 320 you get about 30%. So that's not bad. So between 310 and 320 you get a good portion of the energy, the optical energy. And at 14 milliwatts, that's, let's say, let's be conservative and say 30% of 14 milliwatts. Not clack, calc. So 0.3 times 14, so that's 4.2 milliwatts at 320. And then at the receive side, 320, about 50%. So we're looking at about 2 milliwatts of light at the receiver. So what's the sensitivity of this thing? Like, is there a... Oh. Oh, okay. Huh. Okay, so 2 counts per microwatt per centimeter squared. Huh. So this is actually fairly sensitive. And I believe a count is... No, I'm not sure actually. Yeah, this thing is really cool. It was really popular for a while. They stopped making it, unfortunately. There is a replacement, but it's weird. And it isn't as good. But yeah. Quite like it. It's a little device. They used to make another one There's another VML something 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 something. There's also the SI1125, I think, is another one. But they actually don't really have a UV detector. What they have is it basically detects violet light, because it assumes that any UVA, because it's mostly UVA, it basically assumes that any UVA emitter is going to have like a broad spectrum, because it's mostly for like looking at sunlight. So it assumes it's going to be broad spectrum, and it's just going to leak over into the violet range, which makes it kind of not really a UV detector, even though it says UV. It's a little bit like, you know how you get those environmental sensors that say Eco2, and it's like, oh, it's a CO2 sensor. No, it actually can't measure CO2 at all. What it does is it measures gases that also exist as combustion side products, and then then basically calculates how much CO2 would have been produced through those combustion side products based on the concentration that it can see. Which means that if you're a human being sat in a room breathing out CO2, it detects sod all. And this has pissed me off no end during the whole thing about like checking whether air quality is good, particularly with like COVID and everything. It's like, oh, do I have enough, air circulation and everything? Oh, I'll get a CO2 meter, and then this Eco2 meter, because they're cheap and all over the place. And they do lots of gases, so people are like, oh, I'll get one of them because it can sense 5 different gases. I was like, yeah, but it doesn't actually detect CO2, which means that it doesn't give you a good reading on how poor the air circulation is, which means that you can't actually use it to check whether your air is being circulated properly, which is obviously dangerous in this context. Speaking of which, if you missed it, I did actually put. I finally got round to. This is a bit of a tangent here, but me, massive ADHD. I put this thing up on GitHub. So a long while back, I was working on this reverse engineering the HID protocol for this thing, this CO2 logger. You can get. Don't buy them on Amazon because they're like $200 or something absurd. Go get one off AliExpress. They're about $60. But yeah, a while back I reverse engineered the HID protocol for this. Somebody else had done a bit more of it before, but some of the reverse engineering that's like the documentation on it that's out there is actually slightly incorrect. It'll work for most cases, but it's not actually correct. Like the field sizes and stuff. So I figured out a bunch more, and then fully documented the status report, or at least mostly documented the status report. But more importantly, I documented the log report, which means that you can now dump the log info, like all the historical logging of the CO2 meter over HID, which is quite nice. So I'm quite happy that I remembered. Well, somebody reminded me. I forget who it was. Somebody DM'd me about CO2 meters because they remembered that I knew stuff about CO2 meters. But yeah, that prompted me to remember to put this up on GitHub. So yeah, HT 2000 library. So it's a .NET library, but the code is super easy to read. I'm pretty sure, and also I've documented the full HID protocol here. So yay! Right, I might call it a night because it's now 2 a.m. and I've got to be up for a call with work tomorrow. I was hoping to do a little bit more than this. Although what I will do while I'm here is jot this down. What LED is this? This is the. Oh. What kind of name is that? That is a big name. It's not the worst I've seen. Right. This horrific thing. Yeah, that is actually the full product name. I'll put the LCSC part number in there though. Oops. Oh well, yeah, that'll do. For UVB emitter. So I think that's fine. Isn't quite centered around correct wavelength, or it was about 1/7 of it, wasn't it, that gets through, because it starts off at around 14 milliwatts of optical power, and then by the time we're done, we've got about 2. So yeah, it's about 15% in it. So I think that's quite reasonable. Yeah, okay. So that's quite cool. Okay, yeah, I think that's that gives me something to start with. Obviously, the white LED and the light sensor there. What I will probably do is just go for a very generic white LED, probably something that's like half decent, with like a decent broad spectrum. See if I can find something that's marketed as like a SAD light or something. With like a nice or something with like a really nice CRI, a high CRI LED, and then use that because a nice broad spectrum LED is good for getting a good detection response. And then the sensor will probably be just a cheap like daylight sensor, although maybe not a daylight sensor, because I think they mostly focus on like UV because of the kind of specifically detect daylight, but something with a reasonable spectrum, but probably just like an I2C thing. I'll have to have a look at that. But yeah, so what is technically wrong with my diagram down here now is, other than this, horrendous drawing on the right, which I'm going to rub out because what a mess, is that there are actually 2 LEDs there. Yeah, there are some pretty good ones that are decent bit depth on the intensity detection. Yeah, not bad at all. But yeah, so what this will do then is it will flash the IR, measure it, flash the white, measure it, flash the UV A, measure it, flash the UVB, measure it, and then that will give a spectrum, effectively, like a very crude spectrum with 4 wavelengths or 4 spectra, I guess. But yeah, I do need to investigate the UV and IR optical pass filters. If I can get a notch filter for the specific wavelength that I want, that would be ideal, but I suspect I'll end up going with like crude low pass, high pass filters because they'll be cheaper. Like, I think optical notch filters are actually quite pricey, but I don't know. I'll have to look into it. But yeah, so I guess that's pretty much everything for the moment. Yeah, I will hopefully be back streaming some more work on this. Yeah, okay, so RGB LEDs. Sorry, just before I close off, something that David said in chat. RGB LEDs are something I thought about with an I2C color center. Yes, that is something I could do, but I don't think there's a lot of value in it because a reasonably wideband, even a crap white LED is going to cover all of those wavelengths anyway. And I don't think, because the optical transmissibility of visible light is going to be pretty much even across all of the like across the fog, because if it wasn't, it would like change your color perception in the room, and I don't think it really does that all that much. Like I don't think it skews it that much at all. I mean, it could be interesting, but I think for just simplicity, I'll stick with white and just a white LED detector, rather than trying to go with RGB. Yeah, it'll probably just be easier, unless it works out cheaper that I can get an RGB LED detector IC breakout and an RGB LED breakout, like as separate boards. If that works out cheaper than adding it to the existing board and like having a but I've already got to have two PCBs anyway, I think, because of the UV detection. Wait, no, the UV detection is being done on a breakout anyway, but it's the IR detection, I believe, that I need on an opto coupler. Not opto coupler, photodiode. So I need two PCBs anyway. Yeah, I don't know. I will probably end up just using a white LED. But yes, anyway, I've got to head off. Hopefully I will be able to stream a bit more on this later. And yeah, thanks for hanging out. See you all soon.